Hello.
Yeah, we are live. You can see the attendees. So, welcome everyone to this fourth episode of the MIDI Infrared Discussions webinar series. I'm your host, Simone Deliberato. Just a few words of introduction. The MIDI webinar series aims to offer to the different communities working on MIDI infrared nanophotonics an opportunity to showcase results and foster collaborations. Before the pandemic, we were working to organize a physical conference on Phonon Polaritons, so we decided to focus the first batch of speakers on Phonon Polariton science and technology. According to the feedback we will receive and to the constantly evolving COVID-19 situation, we aim to then extend the focus to other technological platforms, such as intersubband Polaritons and MIDI infrared plasmonics. In this fourth installment, we are honored to have with us today Dr. Alexander Paarmann. Alex started his career in Canada, becoming an expert of ultrafast spectroscopy, and since 2014, he has been a group leader at the Fritz Haber Institute of the Max Planck Society in Berlin, where he pioneered the study of nonlinear properties of phonon polarities. Some practical information before leaving the virtual floor to Dr. Paarmann. The talk will last roughly 45 minutes, followed by time for questions. In order to ask questions after the talk, you can use the Q&A button on the Zoom interface. You can either just write voice, I will unmute you and you can ask your question, or if you prefer, you can write your question in full in the Q&A box and I will read your question aloud. If you want your name to be cited, write it in the question, please. Also, please note this webinar will be recorded and it could be shared online, including questions. Okay, I'm done. I let Alex start his talk on nonlinear phonon polariton spectroscopy and microscopy. Please, Alex.
All right, thanks a lot. I'll start by sharing my screen now. I hope you can all see it. All right, so thanks a lot for organizing this, Simone and Vincenzo and Stefan not being present, but still thank them. This has been very nice. I've been at least 2 of the 3 last webinars and really enjoyed it. And I'm also very happy that I can now put my piece in here. And the special thing, as Simone already mentioned, is that what we do in my group is basically using tools of nonlinear optics to look at phonon polaritons. And you'll see that how we do this spectroscopically and most recently also in a microscopy approach. All right, but before I start, I like to do this acknowledgement thing first because always in the end I'm running short. So first I want to acknowledge all the people involved in this work. I have a small group, currently 4 people, 3 PhD students and 1 postdoc at the physical chemistry department of the Fritz Haber Institute. This is headed by Martin Wolf. So this is my boss. And there are also 3 previous group members, Rico, Marcel, and Ilya, who contributed to the work I'm going to show. Now we do our experiment with somewhat unique light source, which is an infrared free-electron laser. And this machine that we have at the Institute is run by Sandy and Wieland, so thanks to them. And then basically I rely heavily on many collaborations, and you see basically the 2 previous speakers and all the organizers of this webinar showing up here because I have collaborated with all of them, and I'm very grateful. I'm going to show data that involved all of these people during my talk. All right, and one special thank goes to Eugene Tong, who's a member in our department, but he basically taught me everything I know about some frequency generation, so I'm very grateful about this. You'll see in the end of the talk why this is important. All right, so this is by now on nanophotonics. You have seen 3 webinars, or some of you have seen the previous webinars, so you assume most of it. I still want to give you my own angle on the subject on a sort of general introduction level. What we do in general is we try to confine light to sub-wavelength dimensions, right? And the main question, first question could be why? Why do we want to do this? And the way I see it, we basically have 2 driving motivations to do this. For one, by doing so, by squeezing light to dimensions smaller than they naturally exist, we can increase light-matter interaction, and that will, for instance, lead to better sensing schemes. This is just one example, but the idea is clear: increase light-matter interaction and thereby improve certain schemes. And I'm showing an example of the Hillenbrand group here using hexagonal boronitride nanoribbons and show some molecular sensing of Polaritons in this case. And the second reason that I see why we do this is because by making things smaller, we can also reduce the size of the respective photonic elements to make sort of very small scale photonic circuits and stuff like this. So that doesn't involve the light-matter interaction specifically, but more the sheer size of the structures. And one example here is from the group of Thomas Taubner. Also, Josh Caldwell was involved in this work using hexagonal boronitride, where you can basically build flat lenses, hyper lenses with very small footprint and also very small thickness. So this makes very small photonic elements. This is just one example. Okay, so this is why we do it. Then the question would be, how do we do it? And one way, of course, you could just use refractive optics, meaning you just use material with high refractive index, and that will reduce your wavelengths. But typically in nanophotonics, what people do is to use polaritons. And there are a number of different polaritons. The most established ones are Paarmann polaritons. So I'm just picking one example here. So by using Paarmann polaritons, you can achieve that. You reduce the dimension of the light localization, you reduce the wavelength of light, and then use all the perks that come with it. And now recently, and plasmonics has been around for quite a while now, and there's sort of the majority of nanophotonic papers you will find in the literature focuses on plasmonics. But recently, and this all started essentially with the work by Joshua Caldwell, restarted. There has been some previous work, but it really kick-started again in 2013 with this first seminal paper on Phonon Polariton resonators made of silicon carbide. Okay, so now we have these excitations. I'll come back to what the properties of these excitations are. But the important point now for the rest of my talk is, if we confine light to small dimensions, simultaneously, we will also increase the amplitude of the optical field strengths, right? So this basically comes, you just squeeze the energy in smaller volumes and thereby the amplitudes shoot up. And this is basically what my group is specifically looking at. We're using techniques that are sensitive to these optical field enhancements because by doing any kind of nonlinear optical where our signals scale more than linear in order with the local optical field amplitudes, we will get signals that are sensitive to these polaritonic effects. Okay, and this, so I just want to give you along the way for the rest of the talk. So nonlinear optics gains from sort of nonlinear dependence of your signal on the amplitude of the electric fields in your polaritonic structures. Okay, now just a little bit of background on the surface phonon polaritons. This has been done in the previous webinars, but I think I should still do at least one slide here. So we're on the same page. Most people know surface plasma polaritons, and these excitations emerge at typically at the surface of noble metals. And the fundamental excitation that's responsible for these surface polaritons are plasmons, collective oscillations of the charge carrier density. And this typically leads to, by basically the Drude model, you can write this down quite easily, that up to a certain resonance frequency of the plasma frequency, you have negative permittivity, which leads to very high reflectivity, close to 1 for these metals. That's what makes metal so nicely shiny. And in that frequency range of negative permittivity, then you will have these surface excitations. And now if we go away from the noble metals, but instead to dielectrics, so insulating materials, specifically in polar dielectrics, where you have some polarization inside the unit cell of the crystal, then you get a similar type of effect, but now without any free charge carriers, but instead due to the optical phonons. So you see that here in one example, that silicon carbide, which you will see a lot during this talk, as you have in the previous talks, you get a range with very high reflectivity. So you have a range, the so-called restral range, where your dielectric crystal essentially behaves like a metal. And to understand this, you basically just have to look at what you get in these polar crystals. So there you typically have several branches of optical phonons, specifically the transversal optical phonons. Because of the transversal character of these optical phonons, they are often IR active. And if they are IR active, that means that they are resonance of the dielectric response. That means, and that you see down here, it's actually a very simple model. It's just a Lorentz oscillator that you can write down for these TO phonons. But as a result of this Lorentz oscillator, you see that the real part, the blue curve, is actually negative between the TO, the transversal optical phonon resonance frequency, and the LO. Turns back positive behind the LO, but between TO and LO, epsilon is negative. The real part of the dielectric function is negative. And that leads to this quasi-metallic behavior of these materials in this frequency range. And another way to put it is, because you have negative permittivity between those two resonance frequencies, that means that light cannot propagate inside your crystal. Negative permittivity doesn't allow you to propagate light inside. So, and that's why you also call this region the bulk phonon polariton gap. So you see the bulk phonon polariton dispersion that you can calculate quite easily. This is propagating modes inside the crystal into the depths of the crystal. And in this bulk phonon polariton gap in the restral band, you only get the surface bound modes, which are the surface phonon polaritons. And you see the dispersion relation for any arbitrary polar dielectric crystal. And these are the modes that we're interested in. In particular, what we're interested in, that they live on so the light line is the maximum momentum of light in free space. And you see that this surface polariton dispersion lives on the right-hand side. So the momenta are always larger than in free space, or this gives you large momentum states. And these large momenta of the states is what allows you to actually confine to sub-wavelength dimensions. So, but because these modes live on the right-hand side of the light line, they're always evanescent. And so in general, by just shining light on the sample surface of such a crystal, you will not be able to excite these polaritons. You need some way to actually couple to them. And there are various schemes, and we've seen some schemes in the previous webinars, but I'll just run through them again because we've also worked on these schemes for the large part. So the first one I mentioned already are subdiffractional nanostructure. You can basically just think of the scattering on objects that are smaller than the wavelengths will provide sufficient momentum, large momenta, because small structure, to couple to localized polaritons in this case. Another way, and Thomas Taubman has talked about this in the previous webinar, is that just having roughness or edges on a sample surface, if you use a near field type of approach in your investigations, then you will see these polaritons launch at the edges. So then the edge will provide, by scattering, sufficient momentum to launch the polaritons. But then you also have more far field methods. One is the prism coupling, and we've worked quite extensively on this. And as we've also heard in the first talk, the grating coupling is a way to couple two polaritons in a very controlled fashion. And you see here that I put some references there that we have not worked near field because this is not our business, but we've worked on all the other schemes of phonon-polariton excitation with a particular focus of how we can use nonlinear spectroscopy to look at the field enhancements in these different excitation schemes. And I basically my talk will try to go through these different schemes and try to explain the different works of how this works. All right, now I have to do one slide on the machine because it's somewhat special. So we can do this nonlinear infrared spectroscopy because we have the right kind of light source, the right kind of infrared light source. Because if you want to do nonlinear, you need power. And most people don't have power in the infrared. We do. So this is something special. In particular, this is an accelerator-based machine, and I'm not going to explain you the physics of this, but I just leave you with the specs that are important. For one, it's a tunable laser. We can tune it from the mid-infrared out into the far infrared at reasonably narrow bandwidth, typically. So these are picosecond pulses, but still they're long enough so we have narrow bandwidth. So it's really a nicely tunable narrowband laser to do any kind of excitation spectroscopy. And then it's a high power machine, and sort of the important part for the nonlinear spectroscopy. So numbers maybe don't tell you that much, but it's quite significant. The pulse structure is kind of funky. So we have this 10 Hertz macro pulses that consist of micro pulses, and this is one of the reasons why we can't really do SNUM with this machine, because it's really not cool for SNUM. But that's one of the reasons why we go for the nonlinear spectroscopy, because that works really well even with this pulse structure. Okay, and now in my talk, we'll discuss two techniques. For the most part, I'll focus on second harmonic spectroscopy, and I explain this here now, and then at the end of the talk, I will discuss our recent endeavors in doing some frequency instead of second harmonic, but let's stick with the second harmonic first. Okay, so the way we usually do that experiment is we have two beams at different angles incoming on our sample, and we spatially and temporally overlap them at the sample, and then if our sample will provide it, we will generate some second harmonic. So at half the wavelengths, twice the frequency of light, we'll have in the middle emerging a second harmonic signal, and that signal we just put on an MCT detector and measure it. We measure it as we tune our FEL center wavelengths. So, and if we do this, and now we take our beloved prime sample system, silicon carbide, and we did this before we knew about silicon carbide nanophotonics, I'm going to say. So this was independent that we converged on the same sample system. If we do this in silicon carbide, you basically see a spectrum. So as a function of FEL wave number or frequency, you see two peaks, one in the TO frequency region, one in the LO frequency region. And now you would like to know, so that's the first thing, it works as a spectroscopy because it has features. If it was flat, it wasn't so exciting, but because it had peaks, there's something we can do with it. And then if you look at what actually makes this second harmonic signal, then you see that it actually has two major contributions. One is the nonlinear susceptibility. So this is so-called Chi2. And I should mention here that the silicon carbide has broken inversion symmetry. This is important for us, very important for us, because typically second order nonlinear spectroscopy will have zero signal from the bulk if your crystal is inversion symmetric. So we can use this here quite nicely because silicon carbide and many other of the polar crystals have broken inversion symmetry, and that's why we get actually bulk nonlinear signals of second order. So keep that in mind in terms of for all the rest of the talk. anyhow, so this is a not too small number, plus it actually has a peak at the resonance, at the TO phonon resonances, and this peak in the Chi2 is actually responsible for this peak in the second harmonic. And then we have a second contribution, which on the bulk crystal here is in the yellow frequency range. And this actually emerges not because of Chi2. Chi2 is essentially flat there, but we have this second part, which is the E square. So that's the electric field inside the crystal. And even on a flat crystal, this is not flat. So this is this black curve here. So you do get resonances in so-called Fresnel factors, so Fresnel transmission factors on the flat substrate. And these peaks, they look shallow here, but this is logarithmic. So that's why we actually get these peaks in the second harmonic spectrum. Okay, and you see the intensity is what we measure. So overall, this intensity scales to the 4 of the magnitude of the electric fields inside our material. And this part is what makes this technique sensitive to polaritonic effects, because if we have polaritonic field enhancement and our signal scales to the force power of the local electric fields, we can measure polaritonic field enhancements. So we now will go away from flat substrates for the most part and go into polaritons. All right, and the way we started this was actually with this sort of kickstarted by the seminal paper by Joshua Caldwell. And you see that Stefan Meyer and Vincenzo were also involved in this first study that we got into polaritonics. We first looked at these subdiffractional nanostructures made from silicon carbide. And the important perks that also triggered me to start working on this was that these polariton resonances that you see as these deep and narrow dips in the restral reflectivity spectrum, that these are so narrow because that fitted well to our laser, which is a sort of narrow band laser, and we thought I can fully put all the energy into a resonant mode. And this is really a big difference to most plasmonic systems, because in plasmonics, typically the Q factors of these resonances is much larger. I had looked at plasmonic systems and tried to find like good systems for our spectroscopy, but this really popped up as a very important point. And the main difference here is really that because of the long lifetimes of these optical phonons in comparison to plasmons, this is what makes the damping small. This is what makes these Q factors of the resonances so large. And this is really also what sort of triggered this whole field of phonopolariton, phonopolartonics. Yeah. Okay, and also what triggered me already in the papers back then, there were plots like this one which showed, well, you expect optical field enhancements on the order of 100 in these structures, not homogeneously. Oh, sorry. Not homogeneously, but there in some hotspots. But that was clear. If we have a signal that scales to the force power of the local electric field, then enhancement of 100 will boost us. So that's why we went for that. Okay, and then we actually did the experiment. We got some samples from Joshua and started doing first experiments. So first we basically shot next to these nanostructures on a substrate. You see a spectrum that's sort of similar to what I've shown you in the SEG introduction slide. But then as we move the sample to get the nanophotonic structure into the foci, you see that I have to work on this. Yeah, you see that all these polariton resonances really pop up as strong resonances in the second harmonic signal. And this is normalized. So in fact, we got a lot more signal than we had from these substrate resonances, which were already quite strong, but the polaritonic resonances were much stronger. So this was very encouraging that this technique in principle works to probe polaritonic field enhancements. On top of this, because we have a nonlinear technique with multiple polarizations in the game, we can also play games like instead of doing all p-polarized excitation where we have out-of-plane components in our excitation, to switch to S-pol excitation, and then the spectrum cleans up. So most of the resonances disappear from the spectrum, and only actually 2 in this case are left. And this actually allowed us to also, this is also confirmed with the calculations, but our measurements actually proved this experimentally, that so we see the dipole-like polaritonic resonances where you only have in-plane field enhancements. We only see it solely in these s-pole excited spectra, whereas in the p-pole we additionally also see the ones, and these are the strongest, then where we have out-of-plane electric field enhancement. So this is just sort of a nice part of that the polarizations of our beams we can fool with to probe particular components of the optical field enhancements in our sample or of these polaritons that we're trying to look at. The grain of salt for me for this study was I went in and was hoping that we can actually quantify, put numbers on, so that there's a calculation. Now we have an experiment that can probe that. Can we actually quantify experimentally the magnitude of these optical field enhancements? And basically we had to come to the conclusion that we can't, mostly because you have these inhomogeneous field distributions because of the shape of the mode in these nanostructures, and you don't know enough with the far field experiment to recap onto the actual amplitude. So this was my hope, but it didn't really work. And so in parallel, we also started working on a different excitation scheme where this is much more controlled. And out of these examples that I gave in the beginning, we first focused mostly on the Otto geometry. And this is the PhD of Nikolai. So in the Otto geometry, what you do is you use a prism of high refractive index, which is relatively easy in the IR to get refractive indices above 2. And then you shine in light such that you're just above the critical angle of total internal reflection. So you get total internal reflection, 100% reflection out. However, you have an evanescent wave on the backside of the prism under these conditions. And now if you take this prism with your IR beam in it and bring it close to your polaritonic sample, you can overlap this evanescent wave from the prism with the evanescent polariton wave. And this allows you to couple in a very controlled way to excite the surface polariton on a flat surface. All right. And the beautiful thing about this setup is, well, we have essentially complete extrinsic control over the excitation conditions. So we can basically, our experiment allows us to look everywhere. And the reason why we can is, first, we have a tunable laser, so we can cover the vertical axis completely. Secondly, we can change the incident angle, and we do. So by doing this, you see here as cuts in this dispersion plot, we can cross the polariton dispersion at different points, and we can control this. So we can specifically excite polaritons at a given momentum. And finally, sorry, one click too much. And finally, we immediately designed this experiment such that we can also control this gap here, this gap size, with the distance between the prism and the sample. And you see this here in our picture that we have some motors, so we can push the prism away from the sample and control this. And by now we actually measure this gap with white light interferometry. But this is, for this whole Otto geometry experiment, turned out to be really cool and really important, because this gap will define your excitation efficiency. And if we can control this extrinsically, we can always optimize and optimize for maximum efficiency of the excitation. And to understand this is the easiest ways to look at data. So we take silicon carbide again, and now we start measuring a flectance spectrum in this Otto geometry. First, we push pretty close. So we have a small gap between prism and sample. The overlap of the two evanescent waves is large. And then you see that you get this broad and shallow dip in a reflectivity, which corresponds to excitation of a polariton, but not very efficiently. We excite it, but it's broad, so it's lossy, and the depth of the dip is not very good. And now as we move away, we pull away the prism from the sample, we reduce the overlap between those two evanescent waves. The peak is getting sharper and sharper and also deeper and deeper until you reach an optimal point. So this is the point of critical coupling, where you balance so intrinsic losses of the polariton and radiative losses through that coupling of the two evanescent waves. And this is essentially the optimal way of exciting the polariton. And then if you go even further, then you reduce the overlap so much that you don't couple anymore and your dip depth goes away. And you see here that this is really a very nicely controlled experiment, because you can really go to that point of optimal coupling wherever you are in a dispersion, and this point will vary. All right, so this is the linear part. Now we did second harmonic in the same geometry simultaneously to the reflectivity. And here you see at first a second harmonic spectrum. This is logarithmic scale, so there is a large peak even for this. So if we're really close, there's a large peak at the Polariton resonance. And now as we go away with the prism, similar to the reflectivity, the peak gets sharper and sharper. However, here now the behavior of the amplitude is different. So we were expecting that the blue curve should be the strongest, because that's the critical coupling, the polariton. We have the most energy into the polariton. We should get the most SIG out. However, it didn't look like this. We did this systematically at different incidence angles, so at different points in the dispersion. And basically, you always see this critical coupling behavior of the reflectivity. So always find this point of maximum efficiency of excitation. But the SHG amplitude on resonance always has the same behavior, that it basically just drops as we go away. That puzzled us for quite a while, and until we finally got the reason why this is happening. So just imagine that you are at this point of critical coupling between the two evanescent waves, and now you put a lot of energy into the polariton, and this polariton generates a second harmonic field, which I do in blue here. However, the second harmonic field is at half the wavelength, which also means that it has half the evanescent wave decay length. It's exactly half the decay length of the evanescent wave. And that means that in a situation where you're a critical coupling, your second harmonic wave that you want to couple out into the prism so you can detect it in a far field is actually pretty bad. And that's the main reason we're losing the overlap of these second harmonic waves, and that's why our second harmonic intensity is dropping rapidly. Since we know this, and this is a very well-defined system, we can actually basically account for this in simulations and basically recover the second harmonic that's been generated. This is what you see here, rather than a second harmonic that's been detected. And there we basically find exactly the behavior that we expected, that we basically peak second harmonic generation at the point of critical coupling at each of these conditions. The nice thing is, because that's such a well-defined system and such a well-defined experiment, we can actually now feel confident to put numbers on the field enhancement, and that was what we're very happy about. So out of these sort of matching of simulation and experiment, we can basically plot what kind of field enhancements we get for the in-plane fields and for the out-of-plane fields. You see, this is not humongous, but it's on the order of 8 or 10. Of course, it wasn't expected that it's as large as in the nanopillars, because it's a homogeneous mode, a large volume mode that's just sort of small in terms of its wavelength. But it's a significant enhancement. All right, then only lately, like, well, 2 years ago, I had Marcel, a master's student, start to also look into gratings, inspired, for instance, by Café's great work. And I just want to do one slide here to explain how you can also control the excitation of polaritons in the grating geometry. So just think of your incident light field having a certain momentum, providing a certain in-plane component of that momentum. And now as you shine it onto a sub-wavelength grating, sort of a period of the grating needs to be smaller than the wavelength of the excitation light, then you can calculate what the diffraction orders in terms of the in-plane momentum are. So you see, so pi over a, just in solid state physics standard, and you can basically transfer momentum either plus or minus that grating momentum g, which will give you a total momentum either counter-propagating, so this points in the opposite direction of where you shine your light in, or forward propagating, which is sort of further on, considering the way you shine it in. And this difference, sort of this part here, the kx, the in-plane component of the incident light, this is what allows you to actually tune something by changing the incidence angle. And to illustrate this, just think of the sort of, this is sub-wavelengths grating, so that's why this grating momentum cuts the light line not in the surface phonopolariton region or below, but above. So it has larger momentum than the free space momentum of the light that we're looking at. And now if you change the incident angle, you span up this fan of light dispersions into the minus first diffraction order of the grating and the plus first diffraction order of the grating. And the important point to notice here, or zeros order is also there, but the zeros order doesn't matter because it never crosses the surface phonopolariton dispersion. That's because it's within the light cone, right? That's normal. But the counter-propagating one has an intersection, and it's actually in a strongly dispersive part of the dispersion, whereas this plus first order is more in the flat part of the dispersion. And this is important to note because if we are looking for polaritons, propagating polaritons excited in this geometry, we can look for this dispersion as we change the incidence angle, at least in these sort of sets of parameters. Okay, and then we're poor people, no, we're not, but we wanted to start with a similar grating as Grafé's work, and we actually tried to make samples, but they weren't all good. But in the end, we got really good samples by using gold gratings on a silicon carbide substrate. We checked on simulations that in principle this should work the same way with the same period. We get slight shifts of the resonances, but not significant. And then we got very nice samples from Markus Münzenberg and Greifswald, who has like a 3D printing type of infrastructure. And there we got essentially two types of gratings, one with both with 7.2 micrometer period, but in one case we had sort of a third of the period being the bar width of the gold, and in the second one we had 2/3 of the bar width of the period as gold bars. And then we looked at these two samples with our type of techniques. We had looked at simulations and predictions to try to estimate what the best parameters are for the excitation. And this is basically what we came up with. And then we got the samples and took a look in the experiment. And so here now the data looks like this. So on the bottom, he has the reflectivity. And now it's important what I mentioned earlier. So this is as a function of incident angle. So a mode that you see shifting through, dispersing strongly, is the counter-propagating polariton. Whereas that's hard to see by itself here. There is a little dip here also that we assign to the forward propagating polariton in this case. The forward propagating excitation efficiency is not very good in this case. The counter propagating is decent. Simulations at 100%, but this is sort of reality that in an experiment 50% is actually quite nice. So. So that works in principle, and now we look simultaneously at the second harmonic generation from these samples, and you see similar to the prism coupling, we see peaks that move with the resonance of the counter-propagating polaritons. We also see a bit of a peak at the forward-propagating mode. However, well, you see it on a logarithmic scale, but you also see that these substrate resonances that we just get from silicon carbide are still stronger. So it works, but it doesn't work that great. It's a slightly different, but not much better if we look at this second grating where we have much more gold on the sample. Here you see, well, again, we get decent efficiency of the excitation for the counter-propagating. The forward propagating is kind of hard to say because there's a lot happening in the linear optics here. So there's a lot of modulation because you have mostly gold on your surface and some interference between the silicon carbide and the gold components. So the gold is definitely more than just a momentum transducer in this configuration. However, you still see the propagating mode, so we still excite propagating polaritons. Otherwise, we wouldn't see the angular dispersion. So that's sort of a nice experimental proof that it works. plus now this forward propagating mode. It's hard to see in the linear. Sorry, the switching back between pointing and clicking is still difficult. But that I found actually quite nice, that the linear response is very hard to interpret, but in the second harmonic we see a peak. That's sort of relatively clear. So here we could also argue we see a forward propagating and we see the counter propagating polariton. Still, I was personally very disappointed because I thought that this should just rock. We should just be blasted with second harmonic, because the main reason we didn't get blasted with second harmonic in the prism coupling was this outcoupling issue. This is gone here, I thought. So I thought that we should get a lot, and we don't. And I actually don't really understand yet. We do, it works in principle, but the effect is not as strong as I had hoped. In order to sort of wrap our head around this, or try to understand why this is happening, we did some simulations. Simulations don't always tell you why things are happening. Also in this case, it's not necessarily the case. But at least we can recover the same kind of behavior. So we basically set it up in the same geometry as we have our samples. You see that the reflectivity looks perfect, get nicely dispersed in counter-propagating modes. There's a slightly different behavior for the wider gold bars. But then in order to at least estimate the second harmonic yield, we just essentially integrated over the field enhancement to the force power, like what we in the end detect in our experiment. And you see, actually, if you compare this from the shape of the curves and the relative magnitudes, very qualitatively similar spectra for this sort of brute force estimate of the second harmonic yield. So that basically tells us it's not crap in our experiment. There is some physics to it. The simulations don't necessarily tell us what the physics are, but it shows that this is not any kind of mistake, that we're missing some major part of the second harmonic yield in our experiment, because the simulations predict a similar enhancement. It's not as strong as we were hoping it could be. All right. One interesting aspect that we also observed here, and that to some people in the nanophotonics community might not be surprising, but we're still learning, and so for us it was a little bit surprising, is we observed that the dispersion were actually not exactly the same. And on top of this, we saw that the wider gold bars actually have a somewhat blue shifted dispersion. So you see this offset between the red and the blue. These are the console simulations are the dashed lines. The blue circles are the experiment. This matches quite well. So this fits well together. But the theoretical dispersion, if you just take this sort of momentum transfer idea, sits down here. So for the narrow gold bars, this fits reasonably well, but there's a clear shift for the wider gold bars. And we're trying to rationalize this in some way, and my simple-minded view was, well, maybe we could just think that there is some hybridization, that you basically do some localized plasmon excitation in the gold with the free carriers in the gold, alongside with the mode that you excite in the silicon carbide just from the electric field, so that you get some hybridized modes in this case. And I was trying to see if you have that. So if you have some plasmonic contribution that would actually lead to a blue shift of the dispersion, and just to estimate how much of a plasmonic contribution you need, we just put essentially effective medium type of, so basically just included a Drude term in the silicon carbide dispersion as a simple-minded model. And then we see that sort of to reproduce the slope in the beginning, we need a relatively high number of carriers, but then the shape sort of drops off and gets flatter towards larger momenta. And then we're trying to understand why this could be, and the best explanation we came up with was basically using this very nice paper by Stefan Meyer on effective mode volume estimate. So we applied this idea of effective mode volume and looked at how much of the mode that we're exciting is actually residing in the gold. And we can do this. So this, in the end, it's averaged over the whole area. So it gives you an effective mode length. And this is plotted here, and there you see that actually as you go to larger momenta, basically you excite less of the gold. And if you excite less of the gold, this would sort of at least qualitatively explain why this dispersion sort of drops off towards larger momenta, because the free electrons in the gold are not that important anymore for the mode to get. So this actually brings me, I don't know where I are in time, Simone. Okay. I have 10 more minutes after that, but if that's okay.
Yep.
Okay.
Yes, perfect.
The best part is still to come. I just do a 1-minute sidestep to say that this idea of modifying the dispersion of the phonopolaritons is actually, we've been working on this on multiple different fronts. I haven't talked about this here so far, and I just want to do is like one sidestep that we've worked on, basically using simple heterostructures, the polar crystal, and then a thin film on top of it in order to modify the dispersion of polaritons and make it sort of more suitable to a specific application. And there's basically two cases that I just want to flash here. One with Josh and also Simona, where we looked at a polar crystal thin film on top of a silicon carbide substrate. And then the second where we use a dielectric, just a dielectric layer, not a polar layer on top of a polar crystal. And this was work with Thomas Taubner and his student Andreas, who I've seen in the audience. So hi, Andreas. And basically here we use the autogeometry to just show that we can modulate the dispersion in a very specific way, either through strong coupling, and this is what Josh has also talked about in his webinar, or by looking at sort of index shifted switchable polaritons in the GST on top of silicon carbide case. All right, so if you're interested in that, go look at those papers. We get very nice spectra. We have sort of can change the modes. We have very nice Q factors of the modes and very good tuning figure of merits that surprised us quite a bit. All right, but now to the last part, and I'll try to be quick because I'm kind of slow. I've talked about second harmonic for the most part of the talk, but now we also started working on a complementary approach where we don't use two infrared beams, but instead use one visible beam and one infrared beam. It's also second order, so it's in principle the same concept. And one could ask, why do we do this? SAG, in terms of once you have that laser, the second harmonic experiment is much simpler. Some frequency is much more complicated. The main reason is that this is a completely different laser, and you need to synchronize these two laser sources, one being a tabletop laser in your lab and the other one being the large facility free-electron laser. And that took essentially the whole PhD of Rico to get this up and running, so it's complicated. But what you get is two things. For one, in a second harmonic approach, we detect in the mid-infrared, depending on where we excite, mid-infrared or even long-wave infrared. So the best detectors we are using are MCTs. They are not very good detectors. They're not single photon detectors. If you do this in the SFG approach, your signal emerges in the visible, and you can use single photon sensitivity that is around, and so this is much more efficient. And the second thing, and this is sort of what I want to get to, is spatial resolution. I haven't talked about so far. We're here basically limited by how tightly we can focus our laser. But in the visible, this is actually, if we do SFG, and this is a very simple trick, if we frequency mix the resonant infrared beam and the non-resonant visible beam, and we have the signal emerging in the visible, then in principle, the upper limited resolution is given by this some frequency signal in the visible. So that means this is a very simple trick. Just use mix two light waves, one being very long wavelengths, one being very short wavelengths. The long wavelengths being resonant, the short wavelengths being non-resonant, but just upconvert. But the spatial resolution is determined by the short wavelengths. So this is a very easy way of doing super resolution microscopy in the infrared, because your resonances appear in infrared just by this contrast of the two wavelengths. Okay, And basically we tested this first spectroscopically, went back to our beautiful nanopillars. And what you see is if we get some frequency signal in a very similar way as we had SHG on the substrate, here mostly, sorry, this clicking is, so this is the blue curve, we get some resonances in the LO frequency range. And now as we move the sample such that the nanopillar structures are in the focus, the spectrum changes a lot. The substrate resonances are diminished or are reduced, and we see the Polariton resonances pop up. So qualitatively very similar to what we had seen in the SHG. Beautiful. And now I think, okay, this is a very nice contrast. Let's try to image this. And our brutal first shot was to just focus tightly and scan, raster scan across such a sample. So we have these patches with 50 by 50 micron size, and we just scanned across, sitting at either a monopole resonance or sitting at a substrate resonance or at a dipole resonance. And these are the images. The infrared are kind of blurry. This is sort of limited by the focus size of the infrared. But in the SFG images on top, you see, for instance, here, this patch has different geometry. So only this patch is resonance with the 888 wave numbers, and only this patch lights up in the image, whereas the others stay dark. On the substrate resonance, all of the patches are diminished, so we see essentially the structure in these non-resonant images, and the reflectivity is completely blind. So in the IR reflectivity, you see no contrast because it's subdiffractional structures and they are not resonant anymore, but the SFG gives you contrast. So this was good. This was our first shot. And actually that was just on a technical side, the first experimental demonstration of doing SFG microscopy in that wavelength range. Up until then, everybody had done this max at 3 micron. We were the first to do this at 10 micron. We can in principle do it at longer wavelengths. At the same time, it was also not very smart to do it like this, because one can also, well, think about it and say, well, it's not that smart an idea to take this high power, low repetition rate laser and focus it tightly on anything, because you'll burn it. We did burn it to some extent. It was very strange, self-limiting melting of the nanopillars in some of the regions. But it's clear it was not the best solution forever. And instead, we already proposed then that we would like to instead use a wide field microscopy approach. So use large spot sizes of the excitation beams and get the spatial resolution out of the imaging system. Now we are slowly there that we actually do this. As you see in this image, because we do typically SFG in grazing incidents, this is not so trivial to do this imaging, because you have this focal plane distortion from the grazing incidents. There are some solutions already provided a while ago, but we were saying basically we go simpler, at least for silicon carbide with the symmetry of the Chi2 tensor. We don't necessarily need the visible to go in grazing, so we can also go with the visible through the objective in normal incidence. That makes the experiment much easier, and actually also much easier to get good resolution. And this sort of, if I'm showing this here in the photograph where you see how this microscope actually looks in reality. There's your camera. Okay, and this was actually the last measurement we could do before Corona shutdown of the free-electron laser. It's also my last slide. So we did a first shot on similar nanopillar structures. In this case, the period is slightly larger, and they have slightly lower resonance frequencies. These are samples from Josh, by the way. But now the imaging is much different from the previous one. Well, if we go on the monopole resonance, we see the patch lighting up, but we actually see the individual pillars light up and not just the whole patch, because we now have much better spatial resolution. Whereas if we go on the substrate resonance, we see everything light up and we see a little bit of diminishing, but actually we think that we see it in between the pillars, so the substrate that is sitting in between these nanostructures, and the pillars themselves being darker in this imaging. But this is very much still a work in progress. The two main points that I want to make here, and very happy that this is working so well. One, this this method is really much better than tight focus scanning approach that we first tried, because now we basically see these images live while we do it. And this image that I'm showing here is 90 seconds of integration instead of 4 hours that we took for one of those previous images. And secondly, and you see this immediately, if you just zoom in, I mean, this is running at a wavelength of 11.6 micrometer, and we already have a resolution better than 1 micrometer. So we really image the subdiffractional nanostructures and the field enhancement in these subdiffractional nanostructures with a subdiffraction resolution, just by means of nonlinear optics. All right, and this brings me to the summary. So I'm sorry for being somewhat late. I've shown you multiple schemes that we've been following of using nonlinear optical approaches of spectroscopy and microscopy to look at phonopolariton resonances in various different excitation schemes. And I hope I've shown you that we have experimental access, in some cases quantitative, in some cases qualitative, to these polaritonic field enhancement, and that we can also use this idea of frequency mixing to very different wavelengths beams to do super resolution microscopy, and can also look at nanophotonic structures with this approach. And then I'm done, and I thank you for your attention. I'm very happy to take any questions.
Thank you, Alex, for this interesting and very pedagogical talk. Very much appreciated. It's quite impressive what you can do with your free electron laser. It's an impressive machine. I had the pleasure of visiting it, even doing an experiment inside it. Okay, the floor is now open for questions. We have already 2 of them. The first is a question from Xiao. People know that surface plasmon polariton and surface phonon polaritons are either collective excitation of free electrons or phonons. However, both electron and phonon concepts arise from atoms or molecules or a period arrangement of atoms. I have a question. If the light couples to the collective oscillation of the structure of the periodic structure of a metallic array, is this a kind of surface polariton? If yes, what should this belong to?
All right. Thank you for your question. I mean, this relates directly to the discussion I tried to do on these gold gratings, because there it's exactly this point. I go back there. So I've read a lot of literature also on, I mean, there's a lot of papers on sort of what is the nature of modes that you excite in these type of periodic structures, because some people say, well, it's not propagating polaritons, it's some kind of dipole, localized dipole excitations that just happen to be at that frequency. So I don't feel like I'm an expert, point 1. Point 2 is, if I see that this mode is dispersing with incident angle as predicted, then I would call it a polariton, because it propagates, right? It has a direction that I know from the theory, and that sort of the shifting of the resonance with incident angle, this is for me a clear indication that this is a polariton. If it's just a phonon polariton, or if it's a hybrid phonon plasma polariton, I would actually probably call it a hybrid mode. To what extent it's hybridized, it's yet another question. But I'm sure that the gold participates, so it both the phonons and the plasmons in the 2 different locations contribute to the mode. So it's non-trivial to say it's either or. But I think it's a polariton. I would really say because it's propagating. For this forward propagating mode, I mean, it fits in frequency, but still, because there is no shift in the resonance as you change the incident angle, also not predicted, I don't actually have experimental proof that it's polariton. It might just as well be sort of a localized mode there. And the test would be, and I know I've seen Stephanie Lau in the audience, she's done that a lot. If instead of changing incident angle, you change the period of your grating and run a series of different periods, that this mode should shift also. And if it shifts, then you can also assign, so this disperses as expected, so I would call it a polariton. With only 1 period, I cannot make this statement cleanly. So I wouldn't dare to really say. All I can say is fits. So the resonance position fits to what I had predicted, but this is, of course, no experimental proof. And of course, I also think that sort of this clear distinction in many systems is not possible. That's the next thing. It would be nice to call it a name, right? To say you're A or you're B. But I think there, as soon as you go in any kind of multi-component systems, I don't think this always makes a lot of sense to actually say you're A or B, right? I hope that answers the question.
I will add just a comment to what I just said. Absolutely, the description of polaritons as bare components which are then coupled really critically depends on what you consider as bare components. And in very simple systems, there is a clear distinction. When you go into those nanostructured systems, there is really quite a lot of arbitrariness in how you define the bare entities, the bare excitations. Okay, we have a second question. In the starting slides, for silicon carbide nanopillars, we see some dips in the reflectance spectrum. Can you please explain their physical origin? If we have a thin film instead of nanopillars of van der Waals crystal, and can we expect the similar dips?
So point one, is Vincenzo now there? He should answer this. No. There are in these nanostructures, I mean, it's not easy to do an analytical theory that will predict the positions of the dips, but Simone has worked on this and has a bunch of papers on trying to be as precise in terms of an actual model that will predict, depending on the shape, size, where these modes occur. But there's essentially two classes. There's these monopole modes, which are actually having a significant interpillar coupling. So these are actually not only localized modes, but there are sort of collective modes of the whole structure. And these are these dips here. Then there are dipolar modes, which have this, are sort of different excitations with the dipole in plane, left and right of the pillar sides. These are at higher frequency. These are not so strongly coupled between modes, which you see that they don't shift as much as you change, for instance, the period of your array, whereas the monopole modes shift a lot if you change the period. This tells you sort of the collective nature of the one and not so collective nature of the other one. Then there's this little dip here. This is peculiar because this comes from a special thing of 4H silicon carbide. They have this zone folded modes, and there are also some people in the audience who know about this, but I think I keep it short here. Interesting feature that I didn't discuss that we also see in our SAG spectra is below the rest strahl, you actually see a dielectric resonance, because if you look at the dispersion of the dielectric function, you see that towards the TO, the refractive index actually gets really large. It's positive. So it's positive permittivity, but it's very large refractive index. That means that with that size of the structure, you actually get a normal dielectric resonance. We also see this dielectric resonance as pop up as a G spectrum. Okay, I hope that explained the first part. It's non-trivial for these nanostructures to really assign, if you just take a spectrum that you get from a random sample, to say this mode is that, this mode is that, this mode is that. You basically have to do theory to corroborate for that structure what these resonances are. But you have these type of different excitations that I went through, usually in all of those. And if for boron nitride, there is a paper by Joshua Caldwell on these pyramid-shaped boron nitride. So this is the question. You can compare. If you compare, you should compare a sort of pillar-like nanostructure of boron nitride with the silicon carbide pillars. So I don't have the reference, but you'll find it. It's in Joshua Caldwell's paper, I think 2015, Nature Communications, where you see that in boron nitride, because of the hyperbolicity, the nature of the mode is actually significantly different. So we don't have these monopolar or dipolar modes, but you actually have these kind of standing waves of propagating bulk polaritons, and that's sort of from the fundamental physics different, because these are sort of arising from the surface polaritons, whereas boron nitride has these hyperbolic bulk confined or volume confined modes, and that's why the nature of the modes and nanostructures in boron nitride is also different. Still, I think you usually see similar to thin film near field things. You see a series of dips, sort of a series of modes, with sort of a mode progression in these structures, and this also comes essentially from this hyperbolic nature of the boron nitride itself. I hope that answered both questions. Simone, you can leave the question there so I can look again what the question was.
You just have to click on the. You have 3 tabs. On the last one, you see the.
I see it. Sorry. Yeah. Okay. I think I answered it reasonably well.
Next question by Eugenio Calandrini from Paris. Could you comment the spatial resolution of the some frequency generation microscopy? Is it better compared to a SNOM?
No, it's not. I mean, in principle, if you take that concept and go to an X-ray free electron laser, and also bring your infrared free electron laser, then you could frequency mix the X-ray with the infrared, and then you could do imaging with sort of somewhat comparable resolution. I don't think I want to do this experiment. No, I mean, the spatial resolution is limited by the wavelength, so it's limited by the upper limit of this some frequency signal. So if we use 500 nanometers or 532 nanometers for upconversion, meaning our some frequency signal sits at 500 nanometers, upper limit is like on the order of 250 nanometers. This you cannot break because we don't have any sort of STEM type of super resolution component in there. It's just simply the fact that we have more than a factor of 10. We actually have a factor of 20 between the visible and the IR, and this basically defines how much better than the diffraction limited resolution in the IR you can be with that super resolution microscope. It gets better though if we go further to the IR, right? So we still have 250 nanometers fundamental limit, even if we are imaging at 50 microns. So that's sort of a beauty part of it, and we actually intend to go there, but we cannot beat SNOM. It's also not really my intention to beat SNOM, it's the other side. I mean, the beautiful thing about this is it's a wide field, so we accumulate a whole field of view simultaneously. We see everything. We're not exciting locally anywhere. We don't have the tip in there anywhere. It's all optical. And we basically see the whole thing. So I think it's really a complementary technique. And I'm not going to beat SNOM with that approach ever, but it's a really nice complementary approach. And this is the way I see it. And we have selection rules that are different. We can see in-plane fields, which is hard in SNOM. So that's also different. Not in actually in the geometry we do right now, we can in principle also see something there. So, but won't be. So SNOM can go to 20 nanometers. We'll not be at 20 nanometers. That's, or 10 even. We're not going to get there. Okay.
I would say your data are also much simpler to understand, to interpret than SNOM ones.
Yes, that's true. There are some perks if you haven't done it before with wide field microscopy or high resolution wide field microscopy. So you can get lots of funky images. So there's also stuff you have to learn about it in order to properly interpret your images. And we're just in the middle of doing this because this is a very fresh experiment. So I also wouldn't say, well, like this, but yes, still, I think it is much simpler to interpret.
We have another question. Can you use some frequency generation microscopy to image strain fields?
Interesting. I mean, in principle, yes. If I just leave out any kind of nanophotonic structure, For one, if I go to inversion symmetric crystals, so any crystal, then of course I mostly see the surface. And if I have surface phonons, so I have just some dielectric crystal and I have surface phonons at the surface, I will see this. And then if you have strain, in bulk, you will shift phonon modes. That's known, and in principle, this would be susceptible to. If you would also shift surface phonon resonances with the strain in the bulk, that's non-trivial. I don't know, because that's sort of the dangling bond that's looking out of the surface. To what extent this will see the strain in the bulk, I don't actually know. If it's broken inversion crystal, where we get signal from the bulk, I say yes, absolutely. So for instance, if we go to our crystal hybrids that we work with Josh, where you have strain fields, significant strain fields, and you see phonon shifts, of course we image this because we sit on the resonance for where we expect it and it's dark, and then if we go on a resonance where the strain is different, then we see it bright, so we have contrast, and so I don't see why not. That's clear. But you're limited to how much the phonon resonances shift if you look at phonons. If you don't have phonons, I don't know. I don't think then you actually have, so strain in a metal film, I don't think you have a good contrast mechanism that will give you a strain information. I think then it's much better to use other methods. I hope that also answered the question.
Do we have other questions? Please feel free to ask. Let's wait a few seconds. Well, if not, I would say that with this we are done. We all thank Alex again for this really great talk. And we hope you will be with us next week. After 4 other experimental talks, next week we will have a theoretical one by Jakob Hurgin titled Plasmon, Phonon, Plane Dielectric, or a Metal Structure, What Works and Where? An energy balance approach. If you want to really understand the real difference between different mid-infrared platforms, I really suggest you not to miss the next episode. Details of the talk will be announced on my Twitter account and on the event page on Facebook. Thank you, everyone, and see you next week. Bye.
Bye-bye.